Hello and welcome to our Physics 213 Project 2. My name is Nawaf Al-Harbi. My partners are Alejandro Chomero, Aidan Chavez, and Robert Fisher. The topic that we chose for this project is lightning strikes. Lightning is a natural electrostatic discharge that occurs between electrically charged regions of a cloud or between two clouds, or it can happen between the cloud and the ground. It is also associated with thunderstorms, where we have turbulent conditions that cause the charges to separate in the cloud. In this project, we chose to focus more on the electrostatic discharge that occurs between the cloud and the ground, just for simplicity. Also, we will assume turbulent conditions because turbulent conditions initiate this phenomenon and separate the charges in the cloud. So uh, that's the reason for our assumption. My partners will explain this phenomenon and why it happens using the model that we built in physics. Let me start setting up our topic. The positive charges are on top of a cloud, and the negative charges are at the bottom of a cloud. And we have an electrostatic discharge when we have too many charges. So uh, the negative charges are gonna start moving downwards towards the ground, and they will start to form what is called a step leader. And that happens when the charge difference in the cloud is too large. Meanwhile, we will have an upward leader form from the positive charges in the ground. They they form usually from a tall object, so let's say it's a tree in this case, and they will move towards the negative charges. The insulating capacity of the air breaks down, and the electric field will cause the negative charges to start moving downwards towards the positive charges. And the same thing with the positive charges, they will start moving upward towards the negative charges. And once the step leader and the upward leader meet, we will start to see a powerful current shooting upwards towards the cloud, forming what we know as lightning.
Okay, so now for the explanation. So the first of a few physics concepts that are used when lightning strikes is electrostatics. So how lightning forms has a lot to do with electrostatics. Inside the storm clouds that lightning come from, there's a lot of water and ice particles moving around that crash into each other. This eventually causes the positive and negative charges to separate, with the negative charges getting dragged down to the bottom of the cloud. And as more of the charges separate, there's a large buildup of the negative charges, which causes a buildup of electric potential between the cloud base and the ground. And eventually, once this potential keeps building up, it gets so massive that it's enough to break down the air itself, which then allows a path for the lightning to form. Now, another physics concept that's used is electric fields. So with all those separated charges in the cloud, it creates a pretty intense electric field surrounding it. And as the field gets stronger and stronger, it starts ripping electrons off the air molecules, which then ionizes them. This creates a conductive path, which is called a stepped leader, and then that will extend down from the cloud and try to connect to the positive charges on the ground, and that's how lightning is formed. Now, a third concept in physics that is used is current and resistance. And once the step ladder finally makes contact with the ground's positive charge, then that's when you see the lightning strike. That's what the strike is. And through this, there's a massive discharge of electricity that rushes along the path of least resistance. And as this current flows, it keeps ionizing the air molecules along the way. And then this creates a conductive channel. And this is like why we see a large flash across the sky. when lightning strikes. Now to sum it up, how lightning strikes work in general is a lightning strike all starts with the buildup of the separated charges in the cloud. And as those build up, there's higher and higher potential difference between the cloud and the ground. And once this gets strong enough, it breaks down the air and forms a conductive path called a step leader. And the ground's positive charges respond, and then they connect. And that's when you get a massive return stroke of energy, discharging and neutralizing the charges. And that's what then creates the flashes and the sound of lightning.
All right, let's go ahead and look at the sense-making part of this project. First, let's look at the electric potential. Now, when we calculate electric potential of a lightning strike, we can use the concept of electric potential difference between 2 points in an electric field. Now, the electric potential difference, or voltage, is given by this formula, V equals E times D, where V is the electric potential difference, E is the electrical field strength, and D is the distance. Now, for our sense making, we're going to look and put these into their units. So, E is volts over meters, and distance is just meters. So when these cancel out, volts equals volts, so this checks out. Now for a little example, I took the value of 3 million volts per meter for the equation, and then for the distance I did from a cloud to ground of about 5,000 meters. Now calculating this, we get that the electric potential difference of a lightning strike traveling a distance of 5,000 meters through air could be around 15 billion volts. Now, of course, it's worthy to note that this is a very simplified version, but this shows us the amount of strength that the electric potential of a lightning strike has. Now, in talking about that, we have to look into the electric field too. The electrical field in the atmosphere acts as a driving force of the breakdown of air, allowing lightning strike to occur. Now, this force which is called the ionization of air, needs to be 3 million volts per meter. And with this, we could see that once it reaches its threshold, then lightning is able to occur. Now, the electric field strength of these 3 million volts per meter is significant because it quantifies the extreme conditions under which nature overcomes the insulating properties of air to conduct electricity over large distances. This value reflects the critical point at which air naturally resistance to electrical flow breaks down, allowing for a dramatic and powerful phenomenon such as lightning. This is also why we get these little strands off around the area. Now, breaking this down provides a critical threshold for understanding the initiation of lightning strikes. Now, this highlights the remarkable ability of nature to generate conditions under which electrical energy, can be transferred over vast distances, leading to an awe-inspiring and sometimes devastating effects of lightning. Now, going on to current and resistance. Now, to explore the concepts of current and resistance within the context of lightning strike, we'll approach this by examining typical lightning strike and applying Ohm's law. Now, even though the dynamics of lightning are more complex, do not strictly adhere to Ohm's law due to the nonlinear and transient nature of the phenomenon. However, for educational purposes, we can use a simplified version. So to break this down, we have V equals I times R, where I is equal to 30,000 amps and ohms is equal to 10 ohms. Now, for the equation, V equals joules over coulombs, and coulombs is equal to amps over seconds. Amps equals coulombs over seconds, and ohms equals volts over amps. Now, if we put this into the equation, we can see that volts equals this. And upon further simplifying, we see that volts equals volts, so this checks out. Now, for an example, we plugged in 30,000 amps and 10 ohms, and we get 30,000 volts. Now, this calculation provides an estimate of the voltage drop across the lightning channel due to its resistance. Now, it's important to note that in real life scenario, the voltage can be much higher due to the complex nature of lightning, including varying resistance and immense electrical potential difference involved. The calculations for current and resistance in a lightning strike, while simplified, it gives us a glimpse into the electrical characteristics of such an event. The immense current and relatively low resistance of the ionized air path highlight the power of the lightning strikes. These estimates serve as a foundation for understanding the electrical dynamics at play, but should be seen in the context of many other variables and complexities that actual lightning strikes involves. Lastly, for capacitors. For this, we're going to do a comparison between the two. So here we have E equals Q times V. Now the reason for this is since we don't have the capacitance of the cloud ground system, we're using the approach of energy release can also be calculated using charge and the voltage. And now, as we can see here, we have 15 coulombs and 10 million volts. And then we also have the compared capacitor, which we also plugged in to the given equation. Now we can see there's a huge difference in numbers between them. Now this comparison illustrates the applicability of physics principles across different scales and contexts. Now from the design of electrical components to the understanding of meteorological components. This highlights the efficiency and power density of a natural phenomenon and offers insight for potential for technology advances inspired by nature. And again, since this is such a high difference, we could see how crazy that lightning is involved compared to regular energy that we use to our day-to-day lives.
All right, everybody. My name is Aiden, and I'm going to be doing the reflection. So for our topic, we had obviously lightning strikes, and for the reflection, we're tasked with kind of comparing and contrasting this to other similar physics scenarios. So lightning is pretty much like a giant spark, and similar to like other smaller scale electrostatic discharges we encounter, like for instance, touching a doorknob or walking on carpet. It's very similar to lightning, but the scale, the energy, and the consequences of that are very, very different. So the first comparison I want to make is sort of to like a capacitor. Like a capacitor, a cloud accumulates charge until the electric field is strong enough to cause a discharge. And then also in a capacitor, this discharge happens when the electric potential reaches like a certain threshold, similar to a lightning strike. So you can think of this like a circuit. This circuit has two loops and with the switch. When we charge the capacitor in the first loop, it charges until we close the circuit on both, and it can either discharge or charge another object, such as say like a light bulb that you would put in the circuit. The only real difference here is the electric potential of a light bulb and a capacitor circuit versus a lightning strike. We also would need a resistor in the circuit to slow down the current, as opposed to a lightning strike, which is essentially unresisted. But the only resistance to a lightning strike is the air itself. So the difference here is pretty large compared to most normal capacitors we see in everyday life. Another quick comparison we could make would be electric field lines. The concept of electric field lines can be applied to both a charged capacitor and a thundercloud. So the electric field lines point away from the positive charge and towards the negative charge, more commonly referred to as the ground, of course, no pun intended. And the density of these lines indicate the strength of the field. Some of the differences that I'd like to just touch on really quick are the scale. So obviously lightning deals with charges on a much larger scale than something like, say, a capacitor. Another one would be energy. The energy released by a lightning is pretty immense and is capable of powering a household for a month in a single strike. Another thing would be the consequences, as mentioned earlier, and this is just because lightning can cause fires, it can damage structures, it can affect entire electrical grids, and unlike just say like a minor electrostatic shock. The last difference that I want to cover is the discharge path and the duration of a lightning strike versus say like a small circuit. The discharge path in lightning is through air, so that would ionize and become a plasma, and that's what gives it like that crazy glowing look, unlike the direct, physical connection that you have in a circuit with a capacitor. So if just from working on cars, which is my background, something that we can kind of compare it to is like if you have a short-circuited system and you unplug your battery and then plug it back in, you'll see a little spark go from like the terminal to the battery cable. And that's pretty similar to what lightning does in real life. It's essentially a giant piece of plasma coming down. So the discharge from lightning, it also differs in duration. That's another thing. Lightning can be a super quick event and it lasts like microseconds. You can miss it. While a capacitor in say like a circuit, it'll discharge over a very long period depending on what sort of resistance we're seeing. In terms of comparison, that's pretty much it for me. Thank you very much for listening.